We're now starting the afternoon session of the workshop, and it is my great pleasure to introduce Professor Elizabeth Klerman to give her keynote as part of this meeting. She's the director of the Analytic Modeling Unit within the Division of Sleep and Circadian Disorders at Brigham and Women's Hospital. She received her Bachelor of Science from MIT, her MD from Harvard Medical School, and her PhD in Physiology from Harvard University. Her current research focuses on the areas of the interaction of endocrine, circadian, and sleep rhythms in normal and pathological states, and mathematical modeling and analysis of sleep, circadian rhythms, and markers of its function. It's a very great pleasure to have Beth join us here today, and really looking forward to the next hour of her talk. Beth, thank you, yeah, the floor is yours.
Well, good morning, and as you can hear, I'm recovering from a cold, so I'm hoping I'm not going to cough too much, and I'm hoping my voice will make it through. First of all, thank you to Manuel and Nayantara and Dr. Baker for inviting me and in organizing this symposium. The first hour was fantastic, and now we're going to step back a bit for people who have less experience with mathematical modeling, and I was asked to talk about histories, principles, and applications. Here is my conflict of interest disclosure. I've consulted for a number of companies, and my partner owns consulting, but none of these have anything to do with what I'm about to talk. I also want to acknowledge that the content of this talk is the result of many discussions with many people, some of whom are probably or hopefully listening, and I couldn't do this without some or all of them. So thank you all for being colleagues and friends. I'm going to start with an overview about key concepts in modeling. I think there were no equations, except I think I found just one. So for people who are afraid of math but still want to understand modeling, hopefully I can use words and figures to describe the key concepts behind modeling. And then I'm going to give examples of how we use many different ways that we use modeling. So the general paradigm, and I want to compare mathematical modeling to general experimental work, is that we have an mathematical model that we use to design experiments to help us understand physiology and for applications, but also that known circadian physiology experiments and the applications go back and guide these mathematical models. And I'm going to say over and over again, hopefully today, is that it's not just mathematical models that are part of this paradigm, but it's any kind of mental model. And if you're doing an experiment, you have a mental model of the circadian physiology and of the applications that you want to do. And mathematical models are just one subset of this internal or mental model. It's just a little more explicit in one particular way. So examples of mathematical models that we use and others have, Svetlana has already mentioned, are these models of the circadian pacemaker and of neurobehavioral performance. The experiments, for example, are that have been used to help derive the model and are then used, the model is then used to help plan, include phase response, shift work, field studies, forced desynchrony. The applications are to predict outcomes and to test countermeasures. And one of the exciting things that you can do with a model is you can test countermeasures or interventions without having to do every single possible combination, which may be expensive in personnel and finances. And then, as we know, there are effects of circadian rhythms in sleep on performance, safety, and health. So let's talk a little about key concepts in modeling. What's a model? A model, whether it's a mental model or a mathematical model or a model that you hang in your bedroom when you were a kid or whatever, is a simplified description, especially a mathematical one, which is what I'm talking about, of a system or a process to assist calculations and predictions. And as Donna Beersmith said, a useful model should be minimally complex to account for an existing set of data and maximally specific at what its parameters mean in physiological terms. It should not aim at completeness. The essence of a model's usefulness is a simplification of nature rather than approaching the complexity of nature itself. We want to have the simplest way of describing something that's useful. And therefore, all models are wrong because they don't include everything, but some mathematical models are hopefully useful. So a mathematical model is any quantitative representation of how the key elements or the variables are thought to be related. There's your height depends on your age, or something like that. And rather than just saying your height depends on your age, we're going to say this is the mathematical model. This is the mathematical equation that relates your height to your age. Obviously, the relationship changes between the ages of 0 and 20, and then between 20 and 60, and it should be fairly stable. And then the relationship changes a little as you get older, but you still have to put numbers and relationships according to each of these. And therefore, as I mentioned earlier, a model, mathematical model, is a concrete representation of a hypothesis. In the context of biology, models are almost always a simplified representation of the state. The goal is to be parsimonious, just say what you need to say in order to explain most of the model. And as someone said earlier, I can't remember, the problem then becomes when we want to take the model and do predict things related to an individual, because now some of these other factors that aren't in your model may be important in the predictions of the model. There's a key relationship, but they're slightly different, between mathematical modeling and data analyses. So when I use the term data analysis, I'm saying you're trying to extract data from your data set. What's the period, the phase, the amplitude of a circadian rhythm? What's the mean and standard error of your data? What's the relationship? How are they correlated? And remember that the mathematical analysis method you used has a model. If you're going to say that there's a correlation in your brain, there's a correlation, and there's not a regression, which implies something else. Or you try and fit a sinusoid, that means you think the underlying rhythm is a sinusoid. So you have a mental model when you do a mathematical analysis. Mathematical modeling requires this explicit definition of what's involved in the system. This is a linear relationship. This is a sinusoidal relationship. How does the system respond to the stimulus and the interactions within the system? Therefore, in order to do a model, you have to understand the underlying data, and hopefully you also have a complete enough data set in order to do it. So a lot of the problems with modeling about circadian rhythms, effects on a variety of parameters, is that there's not a sufficient data set looking at that particular parameter, stress or blood pressure at all circadian phases. And while not all models should be based on physiology, you're going to hear me, and hopefully the others, say that if you base it on the underlying physiology, that improves the ability to link your results to experiments and to predictions. So here is an example of where your underlying model is important, because all of these four, this is a famous quartet of data, all of these four data sets have the same simple summary statistics like mean and standard deviation. And so you can imagine if you just did a mean and standard deviation, you would say there were no difference among these four data sets. Anybody who's ever trained with me knows that you have to plot the data before you do any analyses, because you can see if you plot these data, even though they all have the same summary statistics, they demonstrate very different underlying relationships. And therefore you would want to use a different analysis method to analyze the data and or decide whether or not there's an outlier. So why do we model sleep and circadian rhythms? As I've mentioned already, to identify key elements of the system and organize our understanding of the system. So if I add hair color to my model of the circadian system, and it doesn't change any of my results, I could say, it appears that maybe hair color is not important for sleep. If on the other hand, my model doesn't fit until I add age, then you could say, oh, well, we think that a key element of the system that we're studying is age. We also use it to explain apparently contradictory results. This is one of the fun things that can happen using models, and I will give an example of that, 2 examples of that later. We use it to generate hypotheses to be tested. This is some of what happens when you have contradictory information, but sometimes you get the model predicts something and you go, oh, really? And you design an experiment to figure out if that's indeed what happens. For countermeasures, you can use models to test or predict outcomes of potential schedules or conditions without having to carry out each possible outcome, condition, or combination, because that can be really expensive. So if you're trying to figure out when you should give light or an intervention, you can use a model to test it and its effects on work schedules. And related to this is to apply control theory. So control theory is you want to achieve a specific result. An open loop is when you, for control theory, is when you basically do an intervention and you see what the result is. But a closed loop is you take that result and then you put it back in your model so that you can apply your next intervention. So you can imagine if you're flying, eventually, hopefully I will, from Boston to the UK, I can do, okay, I'm going to give light at this particular time and see what happens. Or I can say on day one, I'm going to do light at this particular time for this pharmaceutical, see what my new phase is, decide what my new intervention needs to be, and do it again and again and again until I reach the desired phase shift. Or you can use it to combine light and a pharmaceutical. What combination of these interventions produces a phase shift? And you can do that with control. And I'll give an example of that later also. Why, I warned you guys, sorry about the cough. Why is understanding important, understanding physiology important? Well, first of all, as I said before, if you want to apply your results, it's better if your model actually represents the underlying physiology, because then your model can better link it. But also understanding the physiology helps you with model class. So model class is what kind of model are you going to, what kind of relationship are you going to put in your model? Is it going to be linear? Is it going to be sinusoidal? Is it going to be a differential equation producing the limit cycle? And I'm going to show you in the next few slides why if you choose the wrong model class, you can't produce certain kinds of results. And so you need to understand the model class or the equation that you can use in the model. I already mentioned you need data from all circadian phases, and you need appropriate markers of the circadian system as you try and model the circadian system. So if you start with the wrong model class, you can never produce the desired result. And the example of this is what's called type 0 versus type 1 resetting. So the best way to explain type 0 versus type 1 resetting is if you're trying to fly from Boston to go visit Svetlana in Australia. You can either, and that's approximately a 12, let's just say it's a 12-hour phase. If you're going by type 1 resetting, which is a phase only resetting, you basically have to cross every single one of those time zones in order to get to the new time zone. Type 0 resetting, which has two parameters, not just phase, but amplitude, which you can think of as both longitude and latitude, means you can go up to the North Pole where there's no phase, and then immediately go to the appropriate time zone. So you don't have to go through the intermediate time zones. That is type 0 resetting, where you go to what's called the phase singularity, where there's no time zone, and then you go immediately to the new one. If you have a model that is a phase only model, you can never produce type 0 resetting. And we know type 0 resetting occurs in phase. I can provide those papers if you want. So if you're trying to reset, and when I eventually get to travel that way, I'm going to want a model that can do type 0 resetting, because it'll get me there much faster than trying to cross each of the times. And if the model is not valid, then your output simulation. And I'll say this also probably multiple times, your model is always going to produce a result. You have to decide if the assumptions in the model are correct so that the result is appropriate. So, oh, here it is. Your model will always produce a result. You have to apply your knowledge. So here's an example of using a model, and these are the equations I found. So these are the only equations I found. This is an example of a two-state system. And this is an example of a limit cycle, which is one of the kinds of equations that are sometimes used to model circadian rhythms. And a limit cycle has, for this is the famous one of rabbits and foxes. So if we start down here and there's a median amount, the number of rabbits goes up, then the number of foxes will go up, because there's rabbits and foxes eat rabbits, until at such point in time where there's enough foxes that the number of rabbits starts going down. And then after a delay, since there are fewer rabbits, there are going to be fewer foxes. And then as there are fewer foxes, you're going to get more rabbits. So this is a limit cycle, which can go around and around. However, you can perturb the limit cycle. You can suddenly add more rabbits or more foxes, or you can suddenly add fewer. And the system will eventually go back to this limit cycle. That's why it's called a limit cycle. However, it may go back with what's called a delay. So if originally after 2 years you were here, if you've, this point on the graph, if you've perturbed it by adding or subtracting the number of rabbits or foxes, you may now be here on the graph. And this difference, at least, is the change from perturbing the limit cycle. And you can see that when you do an intervention like circadian rhythms. So here's an example of a limit cycle, and these are models that are used for circadian rhythms. So the other reason that limit cycles are frequently used is that it shows that a stable system doesn't have a constant level, which is very important for circadian rhythms because we have a stable system, but it's not constant. And you can predict the long-term effects. So actually, I already talked about type 1 resetting, so I'm going to skip this for a minute. Okay, thank you. So let's move on to key terminology. We're around half the way to examples, so please hang in with me. Model variables are the key elements of the system that we want to read. They're what you can measure, my age, my melatonin response, things like that. Model parameters are what the constants that are used to derive the relationships between the variables. And hopefully they have some sort of meaning. There's a bigger relationship, the coefficient related to age is large or small. Model structure, this is what I've been talking about. What's the hypothesized relationships between the variables and typically model fitting. So once we have this model, we have our model variables and we have our parameters and we have our structure. Now we have to figure out a way to actually get the numbers that we need out of this. We need to fit the model to get the numbers that we can then do to run the simulations. And then validation is we fit this model to a new data set. So you develop the model on one data set and then you fit it to another. You don't get to fit it on the one you used to develop it because that's not fair. Well, it is fair, but it's not right. It's not right and it's not fair. Sorry. This is being recorded. So how do we do this? So we start with this model structure, this idea of this is what I think the model structure is like. These are the equations. These are the important variables. This is the mental model in my mind that I use to define the model structure. And then hopefully I find the right good data set and I can fit the model to the data and I can determine the goodness of fit. The data set. And now I apply the model to make predictions on a different data set. And I see how well the data set fits on the new model. I mean, the model fits on the new data set. And then sometimes you have to improve or extend the model. Now, sometimes this happens because there's a new set of data. And I will show an example of that where the Kronauer model was originally developed for light input. And then we got data related to blind people and under very dim light conditions. And we said, maybe we can make a modification to the model for under dim or no light input to predict non-photic effects. So this is an improvement or extension to the model, and you do the whole thing all over again. Unfortunately, sometimes, or fortunately, sometimes you get stuck here and you have to go back to the drawing board and you have to decide that you're going to define the model structure differently or something like that. But it's a very clear way of doing a process, I guess you could say. So if you want an analogy to experiments, you have an idea that I want to do phase shifting and you define the model structure, you choose your animals, you choose the light condition, you do things like that, you do the experiments, and then, the model structure up here is your hypothesis. I hypothesized that blue light is going to have more an effect than red light. I do an experiment by choosing the animals, the lighting conditions. I fit the model my mental model by looking at the results. And then I might go, ooh, this is really not good. And I have to go back and say, my hypothesis is wrong. Or you can say, now that we know this, how can we apply this knowledge to a new data set, not nocturnal rodents, but diurnal humans? Or how does it affect if we want to do shift work or something like that? And then you might have to change your idea, but it's still this experiment is still this basic modeling parameter. It's just a mental model rather than a physical model. So there are a variety of modeling approaches. One is you model the actual physiology, including its detailed components. So Gianni Forger in 2005 did a mathematical model that included basically every molecular component and interaction of the circadian clock known at that point. 73 equations, I believe. And he said, we know that this interacts with this, and it's this kind of equation because it's this kind of interaction, and that's how we did it. So that's why we have to do a mathematical model. A second way is using the principle to understand the underlying behavior. So I've already said that we sometimes use limit cycles to model the circadian physiology. So we know that circadian physiology is either a some people say you can use sinusoid, sometimes people say you can use a limit cycle, you can use something that you know the underlying physiology. And an example of this is the Klerman model, which is already. And the third one is data-driven or statistical fitting. You look at the model and you go, you look at the data, you go, oh, that looks like a sinusoid. Oh, that looks like an impulse function. Oh, that looks like a square wave. Let's fit it and see how well you do. Now you notice the first two are much more closer to understanding physiology, linking to physiology than the last one is, but they're all valid ways of modeling data. Dynamic modeling versus statistical modeling. So dynamic modeling is you change the model over time. And this is usually done using a differential equation or difference equations, such as the van der Waals oscillator, like the Klerman model, like a limit cycle. And sometimes it has some sort of randomness or noise. If you do statistical modeling or curve fitting, those are usually more like a sinusoid. And this isn't dynamic, so the curve can't change with time. You can sort of shift it, but the shape of the curve doesn't change. Physiological level of modeling. I tend to do, and the examples I'm about to give are all organismal model. How does the whole organism, how does the human circadian phase overall affected by my parameters? But there are people, as I mentioned, Danny Forger and others have done biochemical and molecular modeling. People are doing multicellular modeling. How do you synchronize, how do oscillators, the SCN, each of the cells, neurons has its own oscillator. How do you sync them? What happens when they're not synced? Things like that. So you can look at multicellular. And of course, it's going to become increasing evidence now that there's peripheral oscillators are being studied more. How does the peripheral oscillators, what's their modeling, and how does they link back to the central organism? And probably there'll be more added to this list. I think this is the last slide before we move on to the fun part of examples. How do we compare models? So we might want to compare multiple models to each other. You want to know actually how well does data. You want to know how well does it test your hypothesis. You want to compare different models. My model is better than yours. And you also can use it for developing models. So how do we determine which model is best? Sometimes it's obvious. You look at the data and you go, oh, nope, this doesn't fit. Sometimes you could have to design an experiment to differentiate between models. The two models predict very different things. Let's do an experiment and see what happens. Or you can use mathematical metrics, for goodness sake. So some of you probably heard some of these. They're like adjusted R-square, root mean square model, likelihood ratios, things like that you might have heard from standard classical statistics. And then, however, these measures, don't consider model parsimony, because you can always add more and more metrics to the model until it fits really well. Sometimes you overfit. And so you want to sort of, since you want the most parsimonious, the smallest model that will fit things, these measures below, these information criteria, different information criteria, penalize the model for every additional metric. So it says, is the better fit worth the additional model, the additional additions to the model? So these penalize models that have more parameters. Oh, sorry, I thought I was done. Sorry, with this section. How do you implement them? Well, you got to do it by math. And you need to solve the models mathematically. And so you have to do it software. We can no longer do it by hand. And these are frequently done in things like MATLAB or Python. And I know that MATLAB has a whole bunch of packages for doing models. If you want to use a model that somebody has already done, ask them. Hopefully they will share the code with you. They might be willing to share or collaborate with you. You don't necessarily have to write the code all over again. And then if you're doing statistics, the statistical fitting, then you want to use a statistical package. But they're not necessarily good for doing dynamical systems. Okay, finally, we get to examples. And history. So the most famous model in sleep and circadian rhythms is the two-process model, where process C is the circadian process. And you can see here, it's modeled by a slightly skewed sinusoid. And process S is the sleep part of it. And you can see that it's modeled with a saturating exponential up and a saturating exponential down. So, and then the two of them together so that your sleep depends, the timing and duration of when you're awake or asleep depends on where you are between these two models, these two curves, sorry. So this is a log. So if you plot log on a linear scale, it looks like a saturating exponential. So they noticed that slow wave activity decreased across cycles and is higher after sleep deprivation. So it goes up exponentially because this is a log curve. The longer you're awake, and it goes down exponentially throughout your sleep episode. And then they also saw that some metric looked up and down, which looks circadian, which looks sinusoidal. And so they decided to use saturating exponentials and sinusoidals for process C and process S. So they then define these differential equations and then they plotted it. And this is the famous 1982 paper. I'm supposed to talk about history. So here's a history of how this original two-process model had process C and process S. And then they added rise and fall within the sleep episodes relating to non-REM and REM sleep. And then they added it with another non-REM cycle. Or this branch came down, and sometimes people used the two process to talk about performance and fatigue. Sometimes a third process was added, which is chronic sleep, which is sleep inertia. But you can see that the model has evolved many times by many people to answer different questions. But they're all still based on this idea that sleep and wake and a variety of other parameters are affected by both sleep and circadian factors. So across the 1990s, there were lots of, as I mentioned before, lots of models were developed that wanted to be able to apply sleep and circadian principles to performance and alertness for an application. And specifically, they usually wanted to predict fatigue or different cognitive performance. So in order to do that, however, they needed to add chronic sleep restriction to the model. So the original models were just developed on the fact that you might be awake for one long continuous episode of sleep deprivation. But I don't know about you, many more people don't stay awake for 30 hours. Instead, they don't get enough sleep for multiple nights, possibly because they're coughing. But anyway, and so you needed a new model needed to be developed, a new set of models needed to develop, which looked at the effects of chronic sleep restriction, insufficient sleep on multiple nights, instead of one long sleep episode, a long wake episode. So these were then applied commercially. And the safety fast is a famous one of these models. And some elements, certain elements of the model have indeed been validated in the scientific literature. However, some aspects of these models have not been presented in the scientific literature, and so they are not fully revealed, and we don't necessarily know everything in them or how they've been tested, but they're still being used heavily in many transportation and other safety issues. Here's an example of the safety model. This was in a Federal Railroad Administration report, so it wasn't in a peer-reviewed journal. I still love this, where they looked at their effectiveness. So their outcome measure was effectiveness, sort of the inverse of fatigue, effectiveness. And they showed for accidents that were related to human factors, the less effective you were on their model, the higher the risk of a human factors related accident in the railway system. And the more effective you were, the lower the risk. On the other hand, if you looked at non-human factors, so this human factors is presumably falling asleep at the wheel, or whatever you do on a train. Non-human factors would be railroad track, something happened to the railroad track. There's no relationship between their effectiveness measure and the risk of an accident. And actually, they also showed a link with the cost of the accident. So the less effective you were, if you had an accident, it was more expensive. Here's something from the Ackerstad group, where their outcome was Karolinska sleepiness scale, and they showed that the more sleepy you were, you had a increased odds ratio for a car crash injury. And it was modified by whether or not you'd had alcohol. So here's another example of using the basic two-process model, adding some sort of outcome related to sleepiness or effectiveness, and using it to produce risk of an error or an accident. As was mentioned earlier today, the problem with many of these is that they've been tested and developed at the group level, and there are huge inter-individual differences in vulnerability or resilience, or even in terms of what people are exposed to. Many of these models don't include whether or not you've had caffeine, whether or not you're up the night before coughing, whether or not all these other things happen that may affect your ability to work. So individualizing models is challenging, and it's only been successful in a few cases. It's really, really important future of the field. We need to understand more about this. And my personal experience feeling is that it's going to be a combination of models and some sort of ongoing monitoring, whether it's a wrist-based device or something else, so that you can, in more real time, keep track of what somebody is doing and then do control theory, which we'll get. So also in terms of liability, existing models are a guide, but they should never be used absolutely. We tell people the final decision about whether somebody is safe to work or something like that needs to not be done solely based on the model. The supervisor or somebody else needs to use the model in addition to additional information in order to decide whether somebody's safe. So let's talk about another use of models. Can we understand data that we've collected? So this was a study that we did in college students, and we had the students just tell us when they went to sleep and when they woke up. I'm not going to assume that people know how to read raster plots, so I'm briefly going to tell you what a raster plot is. Let's start over here. A raster plot is time of day across the x-axis and day number across the y-axis. And in this case, the dark bar is when somebody chose to go to sleep. This is also what's called double plotted. So here's day one, here's day one. Here's day two, here's day two. It just enables you to more easily see patterns across days and across midnight. So you can see this person had a pretty regular schedule. They went to sleep around midnight, woke up around 7 a.m. basically all the time. I'm guessing these are weekends where they stayed up later, but they didn't necessarily get to sleep in except here. This person had a very irregular schedule. And they pretty much missed some sleep on some nights, and then the next day they went to sleep earlier. All these things varied. They had an irregular schedule. And in these students, we also did a dim light melatonin onset to look at their circadian phase. And we had noted that these irregular sleepers had a much later DILMO, dim light melatonin onset timing, circadian timing, than regular sleepers. And we wanted to, and they also had different patterns of light exposure. So we wanted to know, can we use the mathematical modeling, a mathematical model of the effects of light input on the human circadian pacemaker to predict circadian phase? And if we take the light dark schedule from the students and we put it into this model, can we predict these differences in dim light melatonin for the regular students versus the irregular students? So we use the Cronauer-Jewett model, and we could indeed predict the differences between, we could predict DILMO, and there was a good relationship between the actual dim light melatonin onset from melatonin and the one predicted from the model. So therefore, we use the model to say how much of the difference in dim light melatonin onset is just due to these students' self-selected light dark patterns, rather than their stress level or what they ate the night before or something else. The third way of using models is to explain apparently contradictory results. So I think this was my second paper, which is a long time ago. When I first started in the field, the forced desynchrony experiments were starting, and they were showing that, and actually, I'm sorry, I don't have time to explain forced desynchrony right now unless people want me to do it later. But there are a series of experiments in which people were put on non-24-hour days. They weren't allowed to self-select their light dark cycles. They were put on these long days so that the circadian pacemaker would separate from the light dark cycle. And under these conditions, the human circadian pacemaker period was 24.2 hours. It wasn't 25 hours, which is what had been seen under self-selected light dark cycles. And so many people in the world at that time, the one thing they knew about circadian rhythms was that the human circadian pacemaker was 25 hours. So we went, can we explain these apparent discrepant lights and these apparent discrepant results? Because they were collected under two different light dark conditions. Under one, people got to self-select their light dark cycle, And under the other, they were exposed to a 28-hour day under dim light conditions. So we used an existing model, and we used the existing light dark schedules, and we predicted what the period would be from each of those conditions. So there were two people who came into the lab who had a forced desynchrony experiment. And we knew from both of these people, from the forced desynchrony experiments, that their periods were 24 points. Then they were brought back into the lab, and they were, excuse me, they were allowed to self-select their light dark cycles. So once again, this is a raster plot, and you can see that this first 3 days, my guess is the first 3 days they had to be on the schedule, and then they were allowed to self-select their light dark schedule. And you can see this person had first had a shorter than 24-hour day, and then sort of went. And this person self-selecting had a longer, skipped for 1 day, and then had a long sleep episode. So we simulate these self-selected light dark cycles. And what was observed from the experiment, because they collected data about period from these, was 24.9 hours or 25 hours. So this is similar to the results seen from the other self-selected light dark cycles. And what we observed from the simulations were also much longer than 24.2. So we can explain this observed period of 25 hours under self-selected light cycles with an endogenous period of approximately 24 hours. So here we're using a mathematical model to explain these apparently contradictory results. If you put 25 hours in as an input to these data, into these sleep-wake cycles, you don't get 24, and I'm sorry, if you put 25 hours into a forced desynchrony protocol, so the reverse of what we showed here, you don't get 24.2 hours out of it. So the parsimonious explanation is that people's human internal period is 24.2 hours, because we can explain both the forced desynchrony and the self-selected results, but not 25 hours, because that can only explain the self-selected, but not the forced desynchrony results. I'm going to skip this because I'm running low on time. This is the underlying physiology. Another example was originally the molecule tau was thought to have one role in physiology. And when Danny Forger did that 73 equation model, he said, no, it looks like tau actually has a different role in the system. So they did the experiments, and then they showed that the model was actually correct, and the field had to rethink about how this particular molecule worked within the circadian pacemaker. 4, we can use the models. Sometimes we modify them. As I mentioned earlier, sometimes we modify them because we have new data or we want to explain new things. So here's an example of wanting to know if some of the individual differences that we see in people, like morning types versus evening types, and their behavior on weekends versus weekdays, can be predicted by these self-selected light dark cycles. So morning people tend to have the same schedule on weekends and weekdays. They can't sleep in, they can't stay up very late on weekends, and it's basically the same. Versus evening people, who usually before the pandemic had to get up and go to work at a particular time, tend to go to sleep later on weekends and tend to sleep in on weekends. So those two behaviors have different self-selected light dark cycles, and you can use those to feed back into the model and say, if we also know that morning people tend to have a shorter circadian period, evening people tend to, can we go back and look and see if we can replicate these results? And indeed we can. If we look at the people who have a shorter period, they have a less of a difference between and weekday than people with longer periods. And if we allow feedback from artificial lighting, you can see the even bigger difference that's seen. And this is what's seen in reports. And the difference between these two is what's known as social level. Another example of modifying the model I mentioned earlier, where the original model assumed a relatively had a certain set of light conditions. And then we did experiments in humans who were either blind or who were under very, very low light conditions. And some of the results made it appear as if there were non-photic cues affecting the human circadian pacemaker. So here, the dotted line, the boxes are the data that were collected from this person on a 24.6-hour schedule. And if the person had a 24.2-hour period, you would expect from photic alone that this is what this is what you would see. that there would be less of they wouldn't move as much, I guess you could say. The circadian pacemaker wouldn't move enough. But if you assume that there's some non-photic part from the sleep-wake cycle or the feeding cycle or the dim light dark cycle, and you add that to the model, you can see that now that predicts this much better. This is a blind person that we put on a shorter than 24-hour day and then on a 24-hour day to see if non-photic cues could affect blind people. And we didn't have to worry about lights at all because we'd already shown that they were totally. And we also knew from this particular person what their intrinsic period was from a forced desynchrony protocol. And so we could make this be shorter than what would be expected from free running. So if there were no non-photic cues, it was photic alone, and this person is blind, and we know what their period is from a forced desynchrony protocol, this is what we would expect to see. They would just drift. But they didn't just drift. And so if you add a non-photic component to the model, it can now predict the fact that they don't just drift. They actually moved a little earlier. It's really interesting. And no, we don't know what it is. And I'd love to be able to figure out what it is before stabilizing. Another way of modifying the models is adding endogenous melatonin to the model. So Anna also has a model where you add exogenous melatonin to this model about light and retina affecting the circadian pacemaker so that you can model how and when you should give melatonin if you want to use melatonin to try and it's a phase response curve for doses of melatonin using the model. And finally, control theory. So control theory, as I mentioned before, is using sort of looping all of this back in to try and find the optimal time. So rather than just doing one intervention, knowing that you're going to do multiple interventions, doing a loop so that you can change the intervention each time to achieve the desired result. So you have an input of a desired phase. You have what's called a controller. And this is based on chemical engineering principles and other engineering principles. You have a controller, which is our model with our equations. Then you have what's called the actuator, which is your intervention. Is it light? Is it a small molecule? Is it something like that? And you have your system, which is in this case a circadian oscillator, and we're looking at the output phase. So we've applied the model with the intervention to the circadian rhythms, we get an output phase. And then we use that output phase and we have to detect that output phase. So we do a melatonin expression test, or we use actigraphy to try and find out circadian phase. And that becomes our new input phase. And we can use that to compare that with our desired phase using the equations, using the actuator. And eventually, hopefully, you'll get your output phase. So here's an example. KL001 is a small molecule that stabilizes nuclear cry, and it's part of the core circadian set of reactions. It's been used in a number of in vitro experiments to try and phase shift the circadian clock. So if we say that we're going to start with this reference trajectory, which is this dotted black line, and we want to begin, they're nicely in sync, and then we're going to have a phase advance of after 12 hours, we're going to have a phase advance of 5 hours, see this phase advance. And then 3 days later, we're going to do a phase delay. Here's the phase delay. And we want to know, when can we give KL01 to optimize the speed at which you recalibrate? And using this control theory models, we can say, okay, this is when we give KL01, this is the amount we give, this is when we give it on day 1 and day 2. But you notice they're similar on these two, but after this delay of 11 hours, you can see that the timing and the amplitude of how much KL1 you give changes depending on where your new phase on that particular day. So rather than applying the same thing over and over again, you modify what you do in order to be able to lock in again. So you now have enough time for questions, I hope, and comments. Your conception of your experimental system and the statistical analyses are both examples of modeling. It's just that mathematical modeling uses mathematical equations as part of this step. Hopefully I've convinced you that it's there are many ways of doing mathematical modeling, and you use different models or different approaches for what you want to do. Sometimes you can use existing models and reach out to somebody who does mathematical models, who usually we're looking for new data sets, and we'd love to collaborate with you. And hopefully I've convinced you of why and taught you a little about how this happens. So thank you very much for your time and attention, and back to my one.
Thank you so much, Beth, for this really, really great and exciting presentation. And I think definitely, I hope that many people in the audience who have not done any modeling or not currently doing it, hopefully it generated some enthusiasm for them to think about it.
And understanding, not just
absolutely, those two, yeah. So let's see, there's a couple of, there's one question from Eva Winnebeck that has come in, and she says, thanks for this wonderful overview. Is there a good dynamic model for use in jet lag data from the field?
Are there other panelists on? Can they say, Svetlana, do you have a good model? There are, I know people have tried using the Kroner model, but for that you need to know light input. So I guess my first question is, what data do you have that you can use to input into the model?
Yeah, no, I second that. Like we have used Kroner model, and I think it's really good, but you do need to know light information, or at least have a good assumption about the light.
Yeah, and then also remember that the models are right now mostly used for average outputs, and they're not as good for individuals.
Exactly. Yep.
But Eva, if you have data, contact one of the two of us, Svetlana or me. We'll see if we can find somebody who wants to work with you. Or there might be other people on the field on the call. I just don't know who they are. I'm not trying to exclude people. Oh, Anne. Yes, I'm sorry. Anne, contact Anne also.
No. Well, actually, I was going to say that there are actually other people in the audience who've done a fair amount of this, because Danny Forger has done a lot on the whole jet lag stuff, and I think Olivia Walsh, who's in the meeting, has also done a fair amount on jet lag and looking at proxies for light from activity, for example.
Absolutely. I'm sorry. I haven't looked to see who else is on the meeting, so I apologize if I haven't mentioned you. Identify yourself in some way, and or contact Eva, and there are lots of people working on this that would probably be happy.
Great. Olivia, I think she's an attendee, but she'll be giving a talk tomorrow as well, so plenty of opportunity, I think, to connect with her as well.
Great.
We have one question from Luke Schlangen, who says, thanks for the wonderful lecture. Would you have any recommendation on how to assess the strength of a circadian rhythm? Would this pertain to circadian amplitude, or is this also related to robustness of the rhythm during environmental challenges? And then finally, are model simulations a useful way to assess the strength of a circadian rhythm, and if so, how?
So for the first question my question is, why do you want to, what's your underlying hypothesis that you want to measure model strength? And so you will use that underlying hypothesis to decide what kind of model you want. And that you're going to use. And this, it relates to the second question. If your hypothesis is that amplitude is important, you can use a model and test whether or not the amplitude of the model affects your outcome. It keeps on coming back to, you can't use a mathematical model without thinking about why you're using it and how you use it. So I'm happy to answer your question, but I'm first going to say, why do you want to know amplitude? What are the conditions that you're using? What's the experiment that you're using? What's your underlying hypothesis? And then it may indeed be true that you can use a mathematical model to see whether or not amplitude is correct. But it will also depend on what your definition of amplitude is. And that's part of mathematical modeling. Is it the amplitude of the core body temperature? Is it amplitude of melatonin? Is it amplitude of something else? And you could imagine that different metrics have different amplitudes. And mathematical modeling forces you to be very specific in what your hypothesis is. And it might be that for some things, amplitude is important. And the reason I didn't ask questions earlier is I told Manuel I was afraid I was going to lose my voice before the end of my talk, and it's happening.
Let's try two more questions, and then we'll leave your voice to recover. I really appreciate that you're doing this under these conditions that you mentioned.
Oh, I'm so happy to be here. Oh, see, I'm approaching Lauren McCall at the moment.
Got one question from Anna Biller. She's asking, could you elaborate a little bit again on how to tackle intra-individual differences, and which studies have attempted to do so?
That's an entire workshop on its own. I'm not even going to try and answer that, because there are so many other people on this call who are actively trying to work on it. And it's a phenomenal question. And as I mentioned, it's where the field is going. We want to know what inter-individual differences, and actually intra-individual differences may make a difference. Is it how much does it matter how much sleep I got last night versus I didn't, or whether I had a cup of coffee or something like that? And it's a great question. And it's going to be the subject, it's the subject of many people's current and future research projects.
So Anna's comment is she'd love to have a workshop on this. So I mean, it's great if a workshop already on the first day generates ideas for new work. Fully supportive of that. We got one question, and let's make this the final one from Nishal Komal Karki. Can you direct me to the paper where you modeled KL001 as control input?
That is Lindsay Brown, BROWN, and Frank Doyle, and I want to say it's PLOS computational biology. It's within the past few years. Lindsay just finished her PhD thesis on using control theory for circadian rhythms, and we just had a paper accepted at IEEE control letters. She's been in PLOS computational biology. She's been in a bunch of others. So look for L.S. Brown and Frank F. Doyle, Francis, I think it's Doyle, D-O-Y-L-E, and there are, I think, 3 papers to date. And if not, just email me and I will forward it to you. Lindsay is now doing a postdoc in Princeton, and we're hoping we're going to hear more from her.
So and then we have, just as the final, maybe the final question that I'd like to ask, concerns, and I think it might be a little bit too zoomed out, but maybe you have some thoughts on this or some view, which is this whole idea of sort of chronotherapeutics and the idea that we think about administration of specific medicines or pharmacological agents in a circadian way. And I want to kind of know what your view is on the role of modeling, both understanding the mechanisms, but also perhaps to push towards a little bit more of a kind of view of personalized medicine. And so maybe you have some, as vague as my question is, maybe you have a complete idea.
Yes, you have to come up with a defined hypothesis. I think modeling at different levels. So there's going to be modeling of pharmacokinetics that should now start including circadian rhythms, because most as far as I know, most drug companies are not using circadian rhythms in their pharmacokinetic modeling. So you would want to start including circadian rhythms in pharmacokinetic modeling. And the modeling, you can think of circadian pharmaceuticals happening at 3 levels. One is, what's the level of the underlying physiology that you're trying to do? So is your heart rate high, or is your heart rate already low? The second is, are there circadian rhythms in the pharmacokinetics? In other words, at some times of day you metabolize it faster than another. And the third is, are there circadian rhythms in your body's response to the drug? Those are 3 different levels, and you could possibly use those 3 modeling to differentiate your chronopharmacologic effect. Does that make sense? So we just published a paper with about the malaria parasite in Science. Joe Takashi was the last author, and John Abel, who was then a postdoc, modeled 3 different ways that the malaria parasite could interact with the circadian clock. And using modeling to match the experiments, we could say, okay, this is the 3 different ways. This is what we think the clock is. So adding modeling these 3 different ways that I just mentioned about how the time of day of medications could affect you would be a great way of understanding the underlying physiology and how and when you're going to do that. And one of the goals, of course, is something like cancer chemotherapy, where the underlying rhythm in the cancer drug may be different than the underlying rhythm of healthy tissue. And can you model when would be the best time to do that? In addition, then there's the whole idea about personalized medicine, which is there some way you can know, is it enough to know I'm a morning person versus an evening person? How precise does your sensor need to be? And that was part of Lindsay Brown's thesis also, was how good does your sensor need to be about circadian phase if you're going to do this control theory where you're going to iterate your next dose, timing and amplitude of your next dose, depending on your sensor, how good your sensor is. And then the third thing is, but when you actually roll this out to a clinic, will the clinic know more than, or the patient be willing to do more than morning versus afternoon? And some of that is a huge implementation issue, and implementation science is a whole part of science that circadian medicine has not paid enough attention to. I've just learned about implementation science, but you can't just say, look, this is the right thing to do and expect it to happen. There are many, many steps in something actually happening. I think this is a great way to answer before I totally lose my voice, because it addresses the issue of modeling, it addresses the issue of underlying physiology, it addresses the issue of how we know whether or not we're doing something right, and then it addresses of how do we actually implement it, which is part of the final goal of what many of us actually want to do, because we want to improve human health and safety. And with that, can I beg off? Oh, there, can I beg off?
Absolutely. Thank you so much, Beth.
Thank you very much.
Great keynote, and also thanks for fielding all these questions from various directions.
Oh, my absolute pleasure. If people want to contact me by email, I'd be happy to talk to them or email them later. Thank you very much.
Thank you so much.